we've got a virtual tour of the NASA Glenn Research Center's Simulated Lunar Operations Laboratory, or SLOPE. And we're really pleased to have here today Erin Rezich, I think is how it's pronounced. Maybe I got that right, who is a GRC Aerospace Engineer. So with that, Erin, take it away.
Thank you very much, Jim. Hello, everyone. Happy to have you at the Glenn Symposium. I'm going to try and find my window here. And all right. So what we have here is the Simulated Lunar Operations Lab at Glenn Research Center. We do a number of different things in this lab. We work on developing soil simulants for both the moon and Mars, which help us conduct more accurate testing. We design and develop different wheels for new innovative rovers. And we also do a little bit of work with ISRU, so in situ resource utilization. And our primary focus there is excavation work. So those topics will come up as we walk our way around the lab. Little tagline there. But this rover that you see up here on the tilt bed, so this bed is in the back of a 60-foot by 20-foot sandbox. It's a real pleasure to be able to work in this lab. But it's on actually 2 dump truck hydraulic systems, and so we're able to carefully control the tilt of this section of the sandbox, which allows us to do different traversals and test what that means for the rovers and what that means for wheel design as well. Up here we have Scarab. Scarab is a tool that's been used for a number of different things and developed by Carnegie Mellon. In this video, you'll see Scarab at probably about 5 times as fast as it actually goes, going through an inchworming motion. And that actually helps it traverse very difficult terrain. The terrain in this scenario is a very high sinkage soil simulant that's actually it's phyllite beads. And those can be found over in this portion of the lab. So we'll make our way over there in a second. Scarab's a very useful tool. Right now it's sporting some of our technology, the spring tire that Goodyear helped develop with us. And so as we make our way over to the right, we'll see a couple more tools that we use around the lab. Here we have an example of a photogrammetry system. So this is important for motion tracking. So when we're doing those traversal tests, we want to understand what the wheels and what the body of any vehicle is doing during those traversals. So we get good data out of those. And then back here, we have the TREC rig, or the Traction Excavation Capabilities rig. TREC is used for, currently it's primarily used for single wheel testing. The whole rig itself is very good at creating repeatable soil conditions so that we can get very consistent data for publications and trying to understand really what's happening at the wheel soil interface. You can also attach excavation equipment to it and get good readings on forces in various different directions. So that's the TREC rig. Right here in the center, we have an example of a novel excavation tool. This one was actually developed at Kennedy. It's called the Badger Bucket. And then, like I said here, we call this the sink tank. So it's filled with phyllite beads, and it's very difficult to traverse, which is why that motion that you saw earlier with Scarab is pretty cool. Because of the nature of the particle size distribution, which is very uniform, and the size shape, which is also very uniform, they're little spheres that are hollow, so it's a very light spherical soil simulant. So it doesn't hold load almost at all. So it's very easy to sink into, which creates a very difficult driving condition. The initial inspiration for something like this was when Spirit and Opportunity were experiencing some issues in traversal during their missions. And so we wanted to better understand what that is like and how we'd be able to traverse that in the lab setting so that we can come up with different ways to either get through it when we're actually are traversing on the moon or Mars, or better ways to just avoid it. So the bevometer is one of the tools that we use to understand vehicle performance in terms of its interaction with the soil. So this was actually a custom rig that we designed, and there are lots of different configurations of a bevometer that can be helpful. And then over here, like I said, we have actually developed a couple of soil simulants, as well as used ones from international. We have some from Canada. The TAN simulant here that you see on the majority of the bed is GRC 1, and this is used to help us study things that are similar to a lunar or Martian or a lunar terrain. So they are not chemical simulants. So the particles that are in here are not necessarily the same types of rocks or grains that would be on the moon. But we've adapted the size distribution and the shapes generally of the particles to account for gravity and mimic traversing on the moon. We've also come up with GRC3, which we use as an excavation simulant. So they are heavily tailored towards specific applications. And over here, so slope has been around for about 15 years, and the original inspiration for the lab actually was designing a next generation wheel. And that started off with trying to understand kind of the state of the art. So there are only a couple vehicles that have actually traversed on other bodies. So one of them is the Lunar roving vehicle, which drove our astronauts around up here, up on the moon on several Apollo missions. And this particular tire is very unique in space history because it is the only compliant tire to ever actually leave the Earth and be driven on another surface. So it's compliant in that it deforms. And it's a little bit difficult to see here, but it's actually a steel mesh. So it doesn't. So in a regular tire, you have a rubber tire, and the air inside the tire carries the load. In this case, you have a steel wire mesh, and so the mesh itself is actually carrying the load of the vehicle. And this was done for a number of reasons. One of them being better traction, and another because it was carrying around astronauts, there is a comfort component there as well. Versus the state of the art right now for Mars is actually this guy right here. So this is the Curiosity wheel, and I'm gonna see if anybody in the question and answer chat can tell me what this little pattern here might be used for, and if it has any significance. So we'll leave that one up to you guys in the chat. But so like I said, this was the state of the art, the LRV tire, in terms of compliant tires for the moon, or compliant tires in space, really. So the Mars tire is rigid. It's all aluminum, and it's machined out of one single billet. And I'll take you up here to our little posters are helpful. So the iterations of the rigid wheel design started when the Mars rovers were very small with the Pathfinder mission. So the vehicle was, a little larger than a dog and tens of pounds, and it worked. The rigid wheel design worked great. And they scaled it up to Spirit and Opportunity, which also performed very, very well, with them being about the size of maybe a golf cart. And then we got to Curiosity, which was about 2,000 pounds and about the size of a small sedan. And some of the weaknesses of this wheel design started to emerge. So we saw there's cracking, and then there's holes in the vehicle. And really what that does is it prohibits us from exploring as freely as we might want to. So a tire that's more durable and can achieve higher tractions and travel further distances really is the goal. So we can go through here. So this is an example. Actually, let's do this one first. We've developed a couple different tires, one of which we did actually test on a Jeep Wrangler out in the West area at Glenn Research Center. And you can see it's performing just fine. Obviously, these are slow speeds at the moment, but we'd like to see them get faster, and something like this make its way into more commercial applications. So the step up from the LRV tire was the steel spring tire. And it was able to carry significantly higher loads, with the LRV tire being 50 to 60 pounds per tire, and this iteration of the spring tire being about 500 pounds per tire. And this is due to the shape of the elements that are actually used in the mesh. So, like I said, we're using springs, weaving springs together to create a mesh, which allows the energy from the applied force to kind of dissipate into different directions, strains. So now you have a torsional component that wasn't really there in your straight wires, and you can deflect a spring much further than you can a single wire for much lower strains. So overall, you get higher load carrying capability. But steel as a material obviously still has its limitations in which you can yield the material. So while it is much stronger, there's still, a maximum load that the tire can carry before the material itself starts to fail. And so that's where we teamed up with our materials folks and introduced the SMA spring tire, so shape memory alloy spring tire. And we're using nickel titanium. And you can see here very, very large deflections on this tire. And it's just basically eating up those rocks. And in that particular rock right there, you watch those springs deform all the way to the rim. And that is something that a steel tire is not capable of doing without yielding the material. So this is our this is the first iteration of where the direction that we're now headed, which is optimizing that shape memory spring tire. In addition, with a couple other options in terms of how the elements look. And so you can get a good look here of what this is. This one happens to be SMA, but this is a spring tire. And so you can see how the mesh works. You get a pattern which affects the traction, and there's an optimization that has to be done in terms of how much soil is going to get through the mesh and things like that. But the SMA addition to this design is really critical because it allows us to kind of supersede a lot of the restrictions that come with steel tires. And so our current design challenge is designing a next generation Mars rover tire using this SMA technology. And for those of you familiar with SMAs, there's some pretty interesting capabilities of it. And so this is actually a thermal video that shows this is an SMA tube. And when you apply load to deflect this, you're actually going to see a thermal reaction happen. And so you can actually see the center of that tube there, it heats up. So you're putting load in and you're actually getting a thermal reaction out. And I'm by no means a materials expert here, but in large part, what's happening is instead of stretching and breaking those metallic bonds like you might do in a standard metal like steel, you're actually rearranging the basic crystal structure of the metal during that deflection. And so that's what allows the reactions to happen, or the thermal excitation to happen, and as well as the mechanisms of that material that allow us to do those amazing things and deflect as much as we did in that first iteration of the tire. So like I said, the tires are a really big component of what we do here in slope. But the one other component of our group that we like to highlight here is, like I said, we do some work in ISRU and excavation. And this is a lab that we've been adding more to and developing. So this is the excavation lab at Glenn. This is the Apex arm, which we are hoping to turn into a standard test methodology for novel excavation tools. Like I said before, we have a number of different simulants that you could try these tools in, as well as gravels and different things. So the idea of the lab is to provide a standard platform to compare against known methods of excavation and then compare them against our new ideas that have turned into prototypes. So it was a brief run through of the slope lab at Glenn. Got one more short video for you here. So another interesting addition, I guess, of SMA, so something that kind of comes with the package, is you have to go through a process called training. So there's an initial amount of deformation that happens, and so you want to actually force that out in a controlled environment so that you have, at the end of the conditioning process, you have the tire that you know is going to perform in a very specific way. And so you guys should be able to find all of these videos on this site after this, after the symposium. So if you want to go back through and watch a lot of these videos in more detail, absolutely feel free. And there's some additional information on the tires in other sites as well. So I think we would be good for a few questions right now. So Kristen Spear got it in the comments there. The tread does, so back on that, the Mars rover tire. So it's a pattern that is used to measure how far the vehicle has traversed. So if there is slip at the vehicle, you would no longer have the standard spacing of the circumference of the tire between each iteration of this print. And JPL got away with a little bit of a fast one here by printing out JPL in Morse code. So that is stamped all over the surface of Mars right now.